Okay. So I'm Sam Scherscher,
And I'm Jakob Davidowitz.
and we're from Cooper Hyperloop, and we're going to present about the brake dyno today. Cooper Union is a small engineering, art, and architecture school in New York City with about 1,000 students. The school has a strong history of engineering design teams, such as motorsports, and Hyperloop came on the scene 3 years ago when the SpaceX competition was still running. Our ultimate goal is to develop Hyperloop technology while also increasing our skills as engineers, giving ourselves experience. So 3 years ago, the team was founded in 2018. Subsequently, we competed in SpaceX competition in 2019. We made it to the top 40 teams, but we didn't present our pod, build our pod and present it in person in California. Following this, the team had a bit of a hiatus for a year. Then we were restarted last in European Hyperloop Week, where we presented our brake dynamometer and some suspension designs. So I'll introduce some relevant background on eddy current brakes. So eddy current brakes, as many of the teams here are probably familiar with, are actually used currently in high-speed trains. They're not just a futuristic technology. And they consist of either permanent magnets or coils that are energized to create an array of alternating poles, which acts like an induction motor and induces poles in a conductive track. And this creates both a drag force and a normal force, which I'll talk about in a bit. And they're currently used in high-speed trains, maglev, roller coasters, industrial equipment, and even gym equipment. So they're pretty widely used. There are some pros and cons of this technology. Some pros are it's contactless, so it provides a force similar to friction, a drag force, without any actual wear and tear on the brakes, and all of the heat is dissipated in the track. And since the vehicle is moving relative to the track, this doesn't result in much heat being dissipated in one piece of material. So it's very good for wear and tear on both the brakes and the track. But some cons are that it's ineffective at low speeds. There's zero braking force if the pod isn't moving. And it also, the braking force depends on the air gap. So it's very sensitive to the length of the air gap between the eddy current brake and the track. So you can derive a mathematical model for the braking force as a function of speed without even solving any differential equations or anything like that. You can just model it as a circuit, and using that, you can derive that the drag force and the normal force follow those equations where A, B, C, D are constants. So we verified this model using last summer using two-dimensional FEM simulations. And you can see that we ran a few different simulations with different air gap sizes, and for each simulation, the data points correspond very closely with the model. So we could just fit those two parameters to those data points and obtain a very close match. So the model is pretty accurate, at least in simulation. However, these simulations are very ideal, and in order to to get actual data we can use and trust, we wanted to get empirical data by running actual tests. So for that reason, we built some small scale models of eddy current brakes.
Okay, so I will go over two different prototypes that have been built by our team. The first one was built. So the first one was built by older teammates in the first year of our team. It was a much smaller scale model, just as a proof of concept. It had only 8 magnets, 4 on the top and the bottom. The one good idea that we kept from that original model was an adjustable error gap, which enabled us to test different braking force using different size error gaps. We also had built a fairly simple brake dynamometer to go with it, and I'll go over that a little bit later. The much more complex model that we built earlier this year, we demonstrated for the first time at the European Hyperloop Week competition, is shown here. We have a number more magnets, 12 on each side. Each magnet having with 12 on each side. This much longer array allows us to mitigate end effects, which will allow us to keep a lot more of the magnetic field inside. This will also much more similarly demonstrate a real world use, in that in our final pod we would have a number more magnets, and the more magnets, the fewer magnetic force lost to end effects. We also added a back iron to channel the flux inward and increase the flux. That way, less of it is lost to going outside of the magnetic field. Lastly, we curved it so that more of the field is attracted onto the flywheel as opposed to going out the back sides. We constructed it out of aluminum and steel, with minimum parts made of most of it made of aluminum to make easy construction with less magnetic parts. So we have 24 magnets made of neodymium 24, which each on their own have about 200 pounds of magnetic force. This is also on a linear slider, which allows it to drag with or to move with the flywheel as it's braking on it. In order to test the eddy current brakes, we built our brake dynamometer, which has a flywheel in order to test it, and we'll also have many different sensors, so we're able to adjust all the different metrics of the brakes in order to test which gives us the best braking force. We simulate the track with an aluminum flywheel, which is 18 inches in diameter, and runs at a max speed of 4850 RPM. These metrics should allow it to simulate roughly a pod going about 270 miles per hour down the track, which would be our projected speed for our final pod. We measure many of the metrics and of the brakes on the dynamometer in order to adjust the metrics of the brakes and understand how that affects the braking force. So our brake dyno is constructed out of steel and aluminum. We use mostly aluminum and the interior parts to decrease magnetic interference from parts outside of the eddy current brakes. We use pulleys and belts for the drivetrain to ensure, and we used to ensure that there is less that the flywheel doesn't spin out of control. And we also built our own actuation mechanism. We use pneumatics to actuate the eddy current brakes. There are a number of reasons for this. First of all, it will have the lightest and least effect on the full pod. Also, it'll continue to actuate even if power going to the system is lost. We also built in a number of different pressure reliefs in order to ensure many fail-safes on the pneumatic system. Also, the air tank has a much higher supply of air than the cylinders needed to actuate, so that even with loss of pressure, the cylinder should still actuate the brakes. We also only have one cylinder, so that as opposed to and the brakes actuate on an angle to avoid having multiple cylinders, which can fall out of sync with each other. We have multiple forms of data acquisition to get the accurate braking speeds, again, to make sure that as we adjust the metrics of the brakes, we are able to understand which has the best effect on the braking speeds. We have a force sensor, right, to measure the braking force, the reaction force that our system is giving. We also built our own fiducial sensors, which reflect light off of reflective tape on the flywheel and measure the amount of time between each reflection to understand how fast the flywheel is going. We also have many safety precautions to ensure the safety both of the system and of onlookers and operators around it. We have a hardened steel shaft to make sure to minimize any small chance that the flywheel can possibly fall off. We also have a plexiglass shell around the operating system, so if any small pieces would possibly fly off, they would not be able to harm any onlookers or operators around it. We also have aluminum mounting plates around the flywheel. So again, if any small pieces fly off, they won't harm crucial components. We have very high factors of safety for all structural components. And lastly, we have a variable frequency drive on the motor to ensure that too much current never goes to the motor and overpowers either the motor or the flywheel from going too fast.
So we built our own. Oh, sorry. There's a bit of an echo. Jakob, you think you could mute yourself?
Yeah, sure. Sorry.
Awesome, that worked. Yeah, so we built our own communication and control system from the ground up for the brake dyno for a couple of reasons. One was to simulate a comms and control system that could possibly be used on a pod, and to learn how to build one for a full pod. So this system runs on a BeagleBone single board computer. This computer communicates with the laptop over USB, and it also communicates with a custom-built e-stop board, which controls both the braking valve and the VFD to turn the motor on and off. And this board is a hardware solution to make sure that the motor and brakes are never on at the same time, and the brakes engage if any contingency or false condition is met. Additionally, the BeagleBone logs and records all of the sensor data throughout an entire test run, and then relays this data to the laptop to be stored in the database. And some of the software engineers on our team built a graphical user interface on the laptop. So the entire thing is controlled from the entire test run is controlled from the laptop. So I'll talk about some potential brake designs that we've thought about and may try in the near or distant future. One of these brake designs is a variable braking eddy current brake, and this can be achieved by varying the air gap between the permanent magnet arrays and the track. And in an actual Hyperloop pod, this would control would be needed over the braking a little bit finer than on-off control. So we would want to control how strong the braking force is. We decided not to invest time into this year because it's not necessary for pod competition. Really, we only need on-off control for now. We've also thought about Halbach arrays. This is a type of permanent magnet array that has a stronger B field on one side of the array because of the geometry. However, it's more difficult to assemble because of the geometry, and the mounting would require a totally different brake design. So we haven't gotten a chance to build prototypes with Halbach arrays yet, but we plan to in the near future. We've also thought about replacing the permanent magnets with electromagnets, and this again would give us more control over the braking force. The downside is that we looked at how much current is required for a coil to fit in the same form factor as a permanent magnet, and we would need a large magnitude of current, which is technically difficult to achieve without a lot of power losses in the windings and in other parts of the system. And because electromagnets require an active flow of current through the coils, they're also not as fail-safe as permanent magnets, which will always provide a B field. Okay, so now I'll show a video demonstration we took last week of the brake dyno. Looks like I have to share a different window. Okay. All right, so a few interesting things to note. So this demonstration wasn't done at our full projected speed of 5,000 RPM. It was the flywheel was spinning at around 1,300. So we're working to get that up to full speed by experimenting with the motor. But the other thing to note is that some of the braking force was supplied by the motor, but since the motor was turned off, when the flywheel spun down, it was actually running the motor as a generator, and so there was some resistance coming from the motor, and you could actually see the eddy current brakes go backwards while the flywheel was still moving. So there was clearly zero force on the eddy current brakes well before the flywheel stopped. But even from this demonstration, there's definitely a lot to be learned about the eddy current braking. So thank you for listening, and welcome to Florida. Any questions?
Hey, I just had a quick question about your flywheel. Just from the video, it looked like it was made of different, or like it wasn't just one disc, but it was made of multiple parts. How did you guys manufacture it?
Sorry for that. So this was manufactured using a CNC. There were a couple of reasons for having manufactured in multiple smaller pieces. The first sort of more practical reason was that the CNC machine in Cooper wasn't quite big enough to build such a large flywheel in one piece. The other sort of afterthought, but also a advantage to having it in multiple pieces was it makes it a lot easier for travel and for moving the dynamometer. When we're transporting it to Europe, we're able to take it apart and reposition it in Spain, which made it a lot easier to fit in the crate, and also made it a lot less susceptible to damage or to destabilizing while it was being shipped.
Yeah, cool. I was just curious because we have a smallish flywheel and we've been looking into getting a bigger one. Did you guys find that balancing the wheel worked quite well? Like, did it spin very true?
Yeah, so we were actually sort of surprised when we first attempted to balance it that it was already fairly balanced, like pretty well, without even having to add any balancing. So yeah, that was sort of a pleasant surprise, but actually was quite balanced, yes.
Cool. Thanks.
So we have a question from the chat. What was the size of the magnet that you guys used, and how much braking force was observed during the experiment?
Yeah, good question. So we used neodymium N42 magnets. So the experiment I showed was our latest kind of development on the brake dynamometer. This week we're actually hoping to get the load cell up and running along with a lot of the comm system. So the comm system has been tested on fake inputs and worked as expected. And we've gotten the fiducial sensor working on its own. The load cell requires some extra electronics to be able to measure the force accurately using a microcontroller. So, yeah, we hope to get the speed force curves by this week or next.
Yeah, from the video, it was hard to tell, like, compared to something else, what's the size of the magnet? Do you have the, the physical dimension of each of the magnets that you guys used for the brake?
Oh yeah, yeah. So the magnets are, I believe, 1/4 inch by 1.5 inch by 1/2 inch. All right, imperial units.
Thanks. Do we have any more questions from the audience? You guys can feel free to unmute yourself and ask a question or type in the chat. Yeah, if there are any more questions coming in, I guess we'll wrap it up here. Thank you guys for the presentation. That was great. Yeah, thank you for attending the virtual showcase.
Thank you all for having us.
Yeah, thank you very much.